MMI711, sequence models and multimedia. This week, we are going to be talking about gated recurrent units. As a matter of fact, we have been preparing ourselves to this point. What we've seen so far was we have talked about recurrency, the feedback mechanism in a neural network, and what it is capable of, why it creates memory, and how it can handle varying length data. What is the difference of a vanilla RNN compared to a feed-forward neural network? Then we've talked about how they can be trained. In order to train recurrent neural networks, we have introduced the idea of unrolling them in time. So when a recurrent neural network was unrolled in time in the sequence dimension, when I say time, I mean the sequence dimension, we had a deep neural network. And that deep neural network, the depth of that deep neural network depended on the length of the sequence size. And we have realized that as the sequence got deeper, it was a deeper network, but it was harder to train. Why? We have covered some mathematical stuff on this, remember, because of the vanishing gradients. Why did the gradients vanish? Because in the procedure of the backpropagation mechanism took the derivatives of the activation function, and the activation functions could create zero gradients, but more than that, the weights were multiplied by itself. And usually the weights are initialized to small values. And as the network got deeper, the multiplication of the weights with itself, the updated weights, became extreme, which led us to this vanishing gradients problem. Actually, this week, we are going to be talking about how this problem is solved for recurrent neural networks. And actually, the solution we have is very powerful, and it is being used widely, practically, in your everyday lives. So this is what we are going to be talking about this week. Let me continue. So we're going to talk about gated recurrent units, namely GRU and LSTM. And we are going to talk about the variants, because we are going to see that there is LSTM. Then there is GRU, which is which has the quite same performance with a bit more efficiency. I'm sorry. Then we are going to talk about its variants, how we can improve LSTM. People have done it in the last decade or 2 decades. These are the things that we're going to be talking about. Okay, let's remember the vanishing gradients problem. I did make an introduction to it, but let's officially go over it once again. As more layers are added to a neural network, the gradients of the loss function approaches to zero. There are mathematical reasons for that. This makes the network hard to train, because the best mechanism we have so far to train neural networks is gradient descent with backpropagation. The layered structure is compatible with backpropagation, and as the gradients die, we are unable to apply this. This was something we already know about deep CNNs. I mean, the fact that as networks got deeper, they becoming harder to train was a fact we have already seen about CNNs or deep neural networks. If you have taken an introductory course, and if you remember, I'm sure in your introductory level course, you have covered this. The fact that deep neural networks were harder to train was an important problem in deep neural network society, which was solved like 5 years ago. I mean, I'm going to get to that. And we have seen previously, in the previous week, truncating the training procedure, the backpropagation through time for sequence models where we unroll the recurrent neural network in time, was a solution. It can solve some issues. But there might be cases that backpropagation in time in a truncated fashion will not work for us, because when you truncate the sequences, you are truncating the dependencies. But we may need to learn so-called long-term dependencies in an input. If a sequence have long-term dependencies, imagine a sequence, a long sequence, the start of the sequence depends on the end of the sequence, or vice versa. In that case, we need something else. We need another mechanism other than truncated backpropagation so that we could train the entire sequence once. So the entire sequence with all its dependence and relationships should affect the training. Actually, in CNNs, a similar problem was solved by the so-called residual networks. If you don't remember residual networks, I'm going to go over it, but most probably in your introductory level deep learning course, you have come across them. Historically, what was residual neural networks? Let me remind you. So before gated recurrent units, how we are going to solve it in recurrent neural networks, I'm going to talk about what residual networks were. The residual network was proposed by Kai-Ming He, a Chinese guy, a famous guy in Microsoft China, in 2015. Remember, in 2012, there came the LXNet. In 2014, there came the GoogleNet, also called the Inception, and VGG 16 and VGG 19. This GoogleNet coming from Google, VGG is coming from Oxford University, VGG group. Both of the studies, both VGG and GoogleNet, had a similar depth, guys. And this was not coincidence, because they were not able to train their network after a depth. I mean, they tried it. They didn't put it in their papers, but they tried it. 711, right? They tried to train their network in a deeper fashion. Believe me, VGG 16, VGG 19 were the published ones, but they tried VGG 30, they tried VGG 50. They couldn't train it because of the vanishing gradient problem. As the depth of the network got larger, as the network got deeper, it was harder to train. Actually, in their paper, Kai-Ming He and others studied this problem in 2015. They started with this discussion. They said that they worked on the CIFAR-10 dataset, which was the earliest datasets that you could work on for convolutional neural networks. They've come up with graphs, training graphs, showing that as the depth of the network got larger, as the network got deeper, the training accuracy, training error did not get better. After some point of depth, it got worse. And they said that this is because of the vanishing gradients problem. They proposed this paper in 2015. But the funny thing is, the solution they proposed in 2015 was a solution that was taken from the LSTM structure. We are going to come to LSTM. I'm going to show you how LSTM solved the vanishing gradient problem for recurrent neural networks. But let us remember residual net, which is something we already know. So we will get the idea. Then it will be easier for us to see how it was originally applied in LSTM. And there's this funny thing here I always say. You first learn convolutional networks. Traditionally, most of the people who are into deep learning first learn deep learning and convolutional neural networks, and they first learn residual neural networks. Residual neural networks were proposed in 2015, and they were inspired by LSTM, which was proposed in 1996. So it is like 20 years before that. So the chronological order you learn the ResNet and LSTM are actually wrong, is actually wrong. First LSTM was found and residual networks were inspired from it. However, since you first learn CNNs and residual networks first, then sequence models, the order you learn it is the opposite. Whatever. What was the solution? The solution was very simple, actually. Kai-Ming He said that for both forward pass and the backward pass, in addition to these convolutional blocks, this is the design of K for residual networks. These weight layers are actually convolutional layers. In addition to these layers, because in a convolutional neural network, in a simple convolutional network, you have these weight layers concatenated serially in LSTM and VGG. He had this skip connection, so-called identity connection, which is the activations you have here are directly passed to here and summed up. So it is like this representation here is summed up here. So this is X. These two layers apply a function, let's say F. So in the end, instead of only having f of x at this point, you have f of x plus x. What does this mean? This means that in the forward pass, imagine you are not able to train anything about f of x. So f of x is a feature extractor. It is not able to extract anything. Well, you don't lose anything. At least you have the previous activations. Maybe the next layer will be able to do it. This makes sense. However, the more important implication is when you think about the backward pass. In the backward pass, you're training the system by backpropagating the partial derivative of the loss with respect to these weights. And because of vanishing gradients or some other reasons that we have talked about the previous week, mathematical reasons, the gradients can die here. However, in a computational graph, when you're applying backpropagation to it, if you have a skip connection like this, the gradients will flow unaffected. So even if the gradients die at this layer, they will be able to flow backwards with this skip connection. And this skip connection allowed Kai-Ming He to construct convolutional neural networks of depth up to 200, 300. And they were much more successful. So this simple skip connection idea allowed the construction of hundreds of layers of deep neural networks at a time where people could only construct or train VGG 16s and VGG 19s, like 20 layers. That's why he had this graph. This graph, this figure is taken from Kai-Ming He's paper for residual neural networks. So, summary, I think this was something you already know, but I'm trying to remind you the concepts. So the problem was, when deeper network starts converging, a degradation problem is exposed. With the network depth increasing, accuracy gets saturated and degrades rapidly. That was the proposed problem in this paper. And this problem is actually the vanishing gradients problem itself. This figure is from the original paper, ResNet paper, Kai-Ming He's He et al. In 2015. By experimentation, they have come up with this idea. So instead of a plain vanilla CNN, they've proposed this architecture, okay? So when they proposed this architecture, they've shown that they could train hundreds of layers of networks, okay? Go read the paper. I strongly recommend you guys read the paper, okay? Because in their paper that they show that this phenomenon is not largely related to overfitting, but vanishing gradients. I mean, because you might say that when you have a larger network, maybe it's not about the vanishing gradients problem, maybe it's about the capacity, but they prove it. They practically prove that this was about the vanishing gradients, and because of this skip connection in the backward pass, the gradients do not get dead. This is very important. So the theory behind the residual network idea was each layer had to learn the representation from scratch, like this, which is correct. As the networks get deeper, they get harder to optimize. So why not let some layers not learn, like a skip connection, so that the gradients may pass backwards. So if you compare the idea of residual convolutional block to a plain convolutional block, the only difference is this identity mapping. This identity mapping in more complex architectures like units is also called a skip connection, because you're just concatenating. Not concatenating actually. Concatenating would mean increasing the depth. We are summing up. We are just adding. Because when you make this addition operation In the backward pass, it means that you're just routing the gradient unaffected backward to this point. Okay? So this was the idea, nothing else. If you didn't know this, this is residual neural networks. And the funny thing is, Kaiming He is a very clever guy. He took this idea from LSTMs, because LSTM is actually this idea being applied to a recurrent neural network. Actually, residual block is a handcrafted design for a convolutional layer in which we benefit a better training performance. And similarly, LSTM is also handcrafted design, GRU as well, which is an improved version of a vanilla RNN with the benefit of better training and larger networks and capacity to handle larger sequences. Okay, any questions about residual networks before I pass to LSTMs, why residual networks work, what is the identity mapping, what is the backpropagation gradient, and etc. Any questions? No, I guess, I mean, at this point, since you're all experienced in deep learning, I'm sure you understand what I'm talking about. And the funny thing is they call this identity mapping a highway of gradients. Because, you know, gradients dying is like traffic congestion. I mean, when there's traffic, you cannot just go, you're stuck. It's like the gradients, your speed vanishing. But if you have a highway, although the gradients die here, there's traffic here. In the backward pass, the cars pass, the gradients pass fast, and you never lose them. So it's like an open highway. What about RNNs? In RNNs, we had this problem. Actually, what Kaiming He worked on for VGG on GoogleNet in 2014-15, we had the exact same problem. As the sequence length gets longer, the representation of the recurrent neural network unrolled in time becomes deeper and deeper. And this creates the vanishing gradient problem. And actually, if we had a handcrafted design like ResNet, we could have been able to solve it. Actually, it was solved with the idea of gating in recurrent neural networks. So in 1960, a guy called Schmidhuber and Hochreiter was his postdoc, and Schmidhuber is a very famous guy. I'm sure you heard of it. He's from Germany. They come up with this idea to construct a recurrent cell, which is a bit complex than an RNN, which has gates in it and allow the gradient flow. And there are these skip connections, which the gradient can flow, and the network can learn deeper and deeper. So what does this have to do with RNNs? Remember what happened when RNNs are rolled in time? Just deep serial blocks. So maybe an advanced RNN, an handcrafted design, which is not a vanilla RNN, but with a residual connection like ResNet, may help us. Actually, it did, because it is the ancestor of ResNet. So this idea is called gating. Okay, recurrent units with gates. Let's make an introduction to this idea. What is gating in a recurrent unit? The vanishing gradient problem that recurrent neural networks suffered is also referred to as the short-term memory problem. Because when the sequence, the only type of sequence you can learn is short, that means you're like the guy in the movie Memento. You only have a short-term memory. You cannot have a long-term memory. So we should solve this. We should be able to find a mechanism to relate long-term dependencies in the sequences we are trying to learn. So simply because if a sequence is long enough, they'll have a hard time carrying information from earlier time steps to later ones. The definition of dependency. So during backpropagation, recurrent neural networks suffer from the vanishing gradients problem, and etc., the thing that we've been talking about. Recurrent units with internal mechanisms called gates can regulate this flow of information, which is the solution to this problem. The very well-known two architectures are the LSTM and GRU. LSTM officially published in 97, but first proposed in 96 by Hofreiter and Schmidhuber, was the first idea for this. Schmidhuber is still one of the very important guys of AI in today's world. And he's like Hinton. He's another Hinton. He's another godfather of deep learning. If Hinton is the godfather of convolutional networks, Schmidhuber is the godfather of recurrent neural networks. And there is an advanced version, which I call the Chinese version, because it's efficient. And in some cases, it's better. It's cheaper because it uses less computation, which was proposed in 2014. We are going to get there. We are going to first see LSTM. Then we are going to get to GRU, why it's cheaper and how does it handle things. Okay, so let's move from RNNs to gated units. In my slides, I'm going to be using these fantastic figures from this guy, Michael Fee. He's a famous guy as well. He's a great AI blogger. Check his blogs. He's preparing fantastic graphics about explaining the fundamental concepts of AI. So check his website. I've got in your PDF slides, you have the links to his YouTube video or blog, whatever. He's a great guy. So we'll start with LSTM and then we'll continue with GRU. Although GRU is newer, it's in architecture-wise, it's simpler. So it's an efficient version of LSTM. So once again, LSTM, RNN in a nutshell. RNN is, you have these RNN. So RNN, he's using these notations, guys. So it's like you have the input coming in from here. You have the state, which is the initial state here. And you have the next state. So this is the first input, this is the second input, this is the third input. While you are feeding different inputs, so in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I've got a 10 long sequence where each sequence is a vector of 3. So the input is a 3 by 1 vector, and I've got a sequence length of these vectors of 10. So as I feed the network, these hidden states are passed between the same cell, which is, as you can see in the figure, unrolled in time. And I've unrolled in time in 10 cells because my sequence length is 10. Okay, this is RNN in a nutshell. So while processing, what you do is you're passing the previous hidden state to the next state. And the hidden state acts as a neural network memory because this state is actually what is passed between the sequence, different sequence elements. So that's the memory, that's the difference of the RNN compared to a feed-forward neural network, something we have been covering for the last 3 weeks, okay? So if you can see it, what you do is you concatenate the input and the hidden state, you apply an activation function. Traditionally, in a recurrent neural network, the activation function is 10H, which is bounded between -1 and +1. This is traditionally the case, actually. This is the actual case, guys. When recurrent neural networks and neural networks came out in the 80s, people were using 10H and sigmoid because these two functions are bounded. They being bounded is actually something bad for us when it comes to backpropagation and gradients, but actually them being bounded is also a good thing, considering they bound the output, so things do not get exploded, the hidden states do not get exploded, so we work on the network in proper values. But it's also something that creates vanishing gradients, but traditionally it's a 10H or sigmoid bounded functions. So this is what recurrent neural network is. The vector goes through the 10H activation and the output is the new hidden state and memory of the network. If you need to create an output from it, you have an output layer here, which you create with different weights and using the, the hidden state, and you create an output, a classification result. But that is not the core of the RNN. The core of the RNN is this, because when we say core RNN, it is input plus hidden states, providing us the new hidden state. Good. So vanilla RNNs traditionally use 10H, just like I said in the previous slide, because 10H activation regulates the values. It is bounded between -1 and +1. This is the function. Okay, so sometimes I go faster than the slide, sorry about that. What is LSTM? LSTM is a handcrafted design. It is just like ResNet in that sense. And actually, it has some connections, but unlike ResNet, it doesn't have a direct identity connection, because in ResNet, there is a direct identity connection. The input would jump in the forward pass, and the gradient would jump back in the backward pass with no condition. This is not the case for the LSTM. That doesn't happen that way. We have a condition using some sort of gates. When I say gates in these slides today, I'm talking about the logic gates. Now, if you're coming from a computer and electrical engineering background, I'm sure you've taken a logic design course. In a logic design course, the gates are the NAND gates, NOR gates, NOT gates. It is like you are allowing some binary inputs, just transforming them. So there's 0 and there's 1. And you get, if you have a NAND gate, you're getting 1 kind of. But these gates, the gates that we are going to be having, here, will not be binary. They are going to be fuzzy logic gates. Fuzzy logic means you will have values between 0 and 1. You will have gray values. So the highway, the identity mapping of residual nets is implemented in LSTMs using fuzzy logic. So it is like not an on-off switch. It is like a switch where you can just turn it on a bit. It will partially allow the flow of information in both forward and backward sense. And it will learn how to do it within the training. How? I'm getting deeper and deeper into it. How to edit? Actually, the answer is the design of the LSTM. And LSTM has a similar control flow as a recurrent neural network, because there are hidden states, and actually there's a self state in addition to the hidden state, which I'm going to be talking about. So it processes the data passing on information as it propagates forward. Okay, that's something general that we can say for a recurrent neural network. The differences are inside the LSTM cell. So if this representation is a simple RNN, vanilla RNN, core RNN, this is the LSTM. So if you look at it, it is not much complicated. I mean, there's a hidden state, there's an input, there's a 10H function, and you get the input. That was the core RNN. In LSTM, we have the red ones, 3 sigmoid functions and 2 10H functions, and a couple of concatenation. This is concatenation, as you can see. If two things are combined like this, like here, they are concatenated. So if there are 2 separate vectors, they are not summed up. They are concatenated. The length of the vector is increased. However, these are actual multiplications and summations. We're going to get there. Okay, so what is it? Similar to the so-called highway of ResNet, we don't have an identity in LSTM, we said. However, we have a fuzzy logic gate which partially controls the flow. And actually, these controls were handcrafted by some solid ideas. Those solid ideas will be the separate gates we are going to see inside the LSTM. We are going to call them different gates like forget gate and reset gate. And those mechanisms are actually intended to make the LSTM to keep information or forget information. How? How to make an LSTM keep information, how to make it forget information. How come these gates is a handcrafted design that allows us to do this? We are going to get into the details. Before I get into these gates, how they function, how they work, let me make a final introduction to LSTM. There is another thing you should know about LSTM. Its main difference from an RNN is, in addition to the hidden state of the RNN, like this one, hidden state, there is another state vector. So LSTM has 2 separate state vectors: the hidden state and the self state. The hidden state is kind of similar to RNN, but the self state is still, it's a state of memory. So because we resemble the states of an RNN, remember to the finite state automata, because states is a type of idea that keeps memory in an automata. In RNN, the state, hidden state, was the memory that we had. Self states are a different type of memory, and actually it is the long-term memory in the LSTM. As you can see, the LSTM stands for long, short, short-term memory. And in the following slides today, we are going to realize that the hidden state will correspond to the short-term memory, just like it corresponds to the short-term memory in an RNN, because RNNs have this short-term memory problem. They cannot have a long-term memory. But in LSTMs, in additional cell states, will provide us the capacity for a long-term memory. So long-term, long, short-term memory, cell states, hidden states, and a design. Okay, so in addition to hidden states, we have a concept of cell states in LSTM. Hidden states of an LSTM is pretty much similar to hidden states of an RNN. Cell states are related to the gates of the LSTM. The gates will create the LSTM. Hidden states are also affected by the gates, but cell states are designed to be affected more dramatically by the gates of the LSTM. The cell states acts as a transport highway that transfers relative information in the sequence chain. And this will provide the cell states the capacity to hold long-term dependencies. As the cell state goes on its journey, the information gets added and removed. So guys, this is the cell state and this is the hidden state. So what kind of an information flow we have here? I'm going to get there. Okay, cell states are the long-term memory. Hidden states are working or short-term memory. Both can be used interchangeably. So they exist both in LSTMs and RNNs, hidden states. But cell states is something that we have in the long-term LSTMs. The gates of an LSTM are designed to create that cell state. So that cell state could learn the long-term dependencies and things that I've already been talking about. Okay, now before we get into the details, the internal details of LSTM, let me make some definitions. In order to understand how the gates of an LSTM function, let's remember how 10H and sigmoid functions function. So 10H is bounded between -1 and +1. Sigmoid is bounded between 0 and +1. Sigmoid being bounded between 0 and +1 is very important for us because, just like I told you, we will be trying to implement the idea of fuzzy logic. Fuzzy logic is a kind of logic where you don't only have the binary logic elements like 0 and 1, you have the gray values as well. So you can have 0.1, 0.2, 0.3. For that matter, sigmoid is a fantastic function because the output of the sigmoid is a fuzzy logic value, whatever it is. It's something between 0 and 1. That's why actually all the sigmoid gates here are actually fuzzy logic gates. And they will be controlling the gating structure in a fuzzy manner. Okay, so sigmoid squishes values between 0 and 1. So this will help us to control the gating. What kind of a gating? For example, if the output of the sigmoid is 0, this here, if you multiply it with the incoming cell states, they will all be 0. Actually, this could lead us to a mechanism like forgetting the previous information, which is something that we might want to. Or if they are all 1, it's like making a pass, just like the highway. So actually, these red circles, which are the sigmoids, are the fuzzy logic gates and the actual gating mechanism in a gated recurrent unit. Good, how does it work? So I'm still giving you an introduction. I'm giving you an idea. We are going to be getting into the very details of how it works. Okay, to understand how LSTM works, actually, we should understand the 4 separate parts in the design of the LSTM. The highway, the first gate, which is called the forget gate, the second gate, which is called the input gate, the third gate, which is called the output gate. As you can see, the 3 sigmoid functions are assigned to 3 different gates. So there are 3 sigmoid functions. Sigmoid functions will create fuzzy logic operations for us, and they create 3 different gates. And we have the highway. And we are clever. Compared to residual nets, LSTM is a bit clever. It can open and close the highway. If it needs to remember something, it will open the highway. If it needs to forget something, it will close the highway. Why would it need to forget something? Well, let me We are going to talk about this in the following slides. This is a good question. Let me not give the answer right away. So, the forget gate. This is a handcrafted design, which was intended to decide, a mechanism to decide what information should be thrown away. Because remember, the cell state is the long-term memory that we keep in this cell, okay? Do we want to keep the previous information, or did we come to a point at the sequence where it is better that we forget all the information behind, or some of it behind? This forget gate functions for this purpose, guys. So what does happen is, you have an input, you have the previous hidden state, they are concatenated here, and is being fed to the sigmoid gate, okay? And the output of the sigmoid gate is actually a vector, which has the same size of the cell state. Usually in an LSTM, hidden states and cell states have the same vector length. This is not necessarily a rule. I mean, you can change the design, but the original design it is. So as you can see, with the combined information taken from the input, the current input, and the precedent state, I create a vector here, which has the same size of the cell state, and I element-wise multiply it. So here I have a vector, right? Here I have a vector. That vector is this, guys. That vector is this. I make this element-wise multiplication. So it is like the cell state is a vector, which holds the long-term information that I'm trying to keep in the network. Each element of the cell state will correspond to a concept in my memory. What kind of a concept, I don't know, because these are neural networks. They are usually non-transparent architectures. But that combined cell state vector will hold that information for me. Maybe at this point of the sequence and at this state, I want to forget some of the information so that I'll be able to learn the incoming sequence better. In that case, this will create a vector with values between 0 and 1, which is element-wise multiplied with the cell state. Some of the elements of the cell state will correspond to elements closer to values 1, because this is a sigmoid. In the end, this is a sigmoid. Which are the parts of the cell state I choose to remember, continue remembering. And the values that are closer to 0 will be the values I choose to forget. So this mechanism actually decides what parts of the cell state to forget. That's why it's called a forget gate. Since I know the design, because these guys, Hochreiter and Schmidt-Huber designed them, I know why it is. This was their design. So this, never forget this. This is a handcrafted design. That's why its name is forget gate. It is intended to just function like this, to choose what part of the cell state is to be forgotten. So it's very simple. At this state, you have concatenation. You have this is a node, this is like a perceptron. You have your weights inside, and you have the bias, and the output is a vector which is exactly the same length as the cell state. Usually these two are the hidden state and cell state are the same length, we said. And we have an element-wise multiplication. And in the end, you have this intermediate cell state, which I'm going to be choosing to call it cell cap, C cap, because we are going to be feeding it to the input gate and the output gate. At this state, C cap is an intermediate cell state in which I have chosen some part of it to forget. I've chosen some part of the cell state to forget, okay? Any questions about the forget gate? Okay, good. We've got 10 minutes, we can continue. Okay, let me continue with the input gate. input gates intention, I told you this is an handcrafted design. So these guys, when they were designing this LSTM, the idea was, after we have decided what parts to forget, now it is time to decide what parts to update and how to update. Okay, so input gate can be also called as the update gate as well. Okay, so input gate does two things. Passes the previous hidden state and the current input. As you can see, this thing is passed. So the input to this fuzzy logic gate is the same input. The input of this fuzzy logic gate is also an input to this fuzzy logic gate as well. So we have a vector created here. Wonderful. And the second thing is, it also passes the same concatenated input to a 10H architecture so that it creates some values between minus and +1, so that maybe it could contribute to the cell state. But still, we have a logic here. We create an input here. We decide how to let it go with a gating mechanism, because we have an element-wise multiplication here, okay? We create a fuzzy logic gate here. We create an updated cell state value. So the output at this point and at this point is the same size as a cell state. They are element-wise multiplied. So at this point, I have what is to be added to the cell state, and I add it. So if you look at the formula, it is this. So first, in the first formula, you have the sigmoid function here and the 10H function here. And you just, this is the yellow formula is this part. This purple formula is this part. And I add them, guys. I add them. When I add them, I obtain the cell states, because this was an intermediate cell state, C cap, remember? I'm going to add it with the newly created value in the update gate, the input gate. I'm going to be having the actual cell state. So this is how I actually choose what to forget and what to keep. Actually, the long-term capability of an LSTM is hidden in this idea. If you provide the network a mechanism to learn what to keep and what to forget, it won't be overwhelmed with incoming data and such that it would just lose the older sequence and will always be trying to learn what is the newer part in it, which is actually the vanishing gradient problem itself. So that's it. That is the mechanism. You also have an output gate, but the output gate will be used to create the hidden state. So after these two gates, forget gate and input gate, actually we have the cell gate. As you can see, add these up, I have the cell state. Sorry. Okay, any questions about the cell state? Because cell state is a creation of the forget and input gates.